Alright, let's look at Bernoulli random variables and their sum. So of course, if xi's are Bernoulli, then with, let's say with parameter p, then the sum of independent Bernoullis is binomial. So this is a binomial random variable with parameters n comma p. So what we want to look at is this sum as Bernoullis are happening rapidly. In other words, n tends to infinity, and I want to show that this random variable will begin to look like Poisson. So very quickly, probability of xi equal to plus 1 is of course p, small p, and probability of xi equal to minus 1 is, or tail is q. This is what we mean by Bernoulli. And so x is the standard binomial distribution, which means probability of x equal to k is n choose k, p to the power k, q to the power n minus k. I want to look at this expression as n becomes large. So once again, probability of x equal to k is n choose k, which I can write in this form, over k factorial, then p to the power k, q, which is 1 minus p to the power n to the n minus k. Now, what I mean by form is that if you look at the expected value of x, this is np, I'm going to assume that their average value remains a constant. So of course, if n becomes large, then p must also become small, such that np is a constant. So that's the assumption. Notice that I'm going to divide this here by n to the power k, so I multiply this by nk. So this of course becomes 1 multiplied by 1 over n, 1 minus 2 over n, etc. 1 minus k plus 1 over n. And then we have a k factorial here. And then you have np, which is lambda to the power k, and 1 minus, I'm going to multiply and divide by n. So this is lambda over n to the power n minus k. So if I pull up everything here, this leads to a probability of x equal to k is 1 multiplied by 1 minus 1 over n, 1 minus 2 over n, etc. A finite number of terms over, let's say 1 minus lambda over n to the power k, also a finite number of terms. Then you have lambda k over k factorial, 1 minus lambda over n to the power n. I brought that n minus k here. But notice that now as limit n tending to infinity, probability of x equal to k is, we need to make n go to infinity. As n goes to infinity, each of these terms goes to 1, a finite number of times, that's 1. Here as n goes to infinity, this is 1, because k is finite. And here, so this is essentially lambda k over k factorial, limit n tends to infinity, 1 minus lambda to the power n over n. And this is of course e raised to minus lambda. So we get the whole thing to be e raised to minus lambda, or lambda k over k factorial, k equal to 0, 1, 2, etc. Here generally this is k equal to, here k equal to 0, 1, 2, etc. up to n, but n goes to infinity, so this goes to infinity, and this is the binomial. So the moral of the story is a binomial random variable where the underlying Bernoullis are occurring rapidly with smaller and smaller probabilities, then this begins to behave like Poisson. So each of this is a rare event. So that's the reason the Poisson also is known as rare events. And if you plot this, this looks like this typically, depending on the value of lambda.